the value for x. That's not what's going on here. This is, we don't get to choose this value. There's one particular quantity that makes those two expressions the same, and we don't get to pick it. We have to find it. But in contrast, functions kind of tell us what's the result if I pick a certain quantity for x. So in my cell phone bill, if I get to choose how many minutes I get to talk every month, well then that determines something. That determines my y value. That determines my total cell phone bill, right? And I think the majority of our time, we dealt with all three of these, by the way, but the majority of our time we spend with algebraic functions, right? But before we go too much further, I wanted to make sure that you understood that these three types of descriptions all kind of fell under the umbrella of linear descriptions. Remember when we talked about that last time? All three of these descriptions were what we call linear. Right? But then on Tuesday, we started to make some progress, because then we kind of made the transition into things that were non-linear. And there's lots of nonlinear descriptions, but in particular, we dealt with nonlinear descriptions that were of a certain flavor. Remember what they were? I'll give you some examples, and then you tell me the more generic word. Like we dealt with monomials, we dealt with binomials, we dealt with trinomials, but the more generic word was what? A polynomial, right? A polynomial, which kind of covers all of those different types: monomials, binomials, trinomials. And there's even some of these polynomials that aren't mono, bi, and trinomials. Like there's four-term expressions, five-term expressions, so on and so forth. There are these polynomials. Okay. And on Tuesday, what did we deal with? Did we deal with polynomial expressions? Did we deal with polynomial equations? Or did we deal with polynomial functions? Which one of those three descriptions did we deal with on Tuesday? Expressions, equations, or functions?
Expressions.
Expressions. We dealt with polynomial expressions. And when we dealt with, let me give you maybe a trinomial here. So there's a trinomial. What did we learn to do with these polynomials last time? What was our main objective from Tuesday? What did we learn to do with them? We learned to factor them, right? So we were able to take a polynomial, and if it could factor, we learned how to factor it. So when we factor, that process takes a polynomial. In this case, it's a trinomial, right? Why is it a trinomial again?
Three different terms.
Three terms, right? It has three terms: x squared, 2x, and -3. When we take this polynomial and we factor it, we take a single polynomial, in this case a single trinomial, and then we rewrite it as multiplication of more than one polynomial. So what we want to do is we want to transform this polynomial into two polynomials, or maybe three, maybe even four polynomials, that are multiplying. That's what the word factor means. Remember, factors are values that multiply, okay? And we learned to do that using three different techniques. Let's see if we can't rehash those three different techniques. The first thing we do when we factor, GCF. We need to look for a greatest common factor, right? And remember, the greatest common factor asks, is there any value that divides into all three terms? In this case, there's not. All right, just quickly reviewing. And then we ask, do the three terms have a common variable? They don't. It's close. That third term spoils it all, right? No GCF. But we should check. And I didn't practice what I preached last time. Remember that last example when I did check for the GCF, and it kind of bit me in the rear end because it was a much more difficult factorization than it should have been. The second thing we need to do is what? What do we need to look for after GCF?
Quadratic trinomial.
Yeah, we need to look to see if it's a quadratic trinomial. If it's quadratic, what characteristic does it have? X squared. This is quadratic. X squared. One of the things I don't think I emphasized enough on Tuesday was we need to be sure that our polynomials are in descending order, right? Remember what descending order means. That means it goes from the largest exponent down to the smallest. This quadratic trinomial is in descending order. Look at it. Look how the exponents fall down. Exponent 2, understood exponent of 1. There's not an exponent on x at all. Exponent of 0, right? It's in descending order. But this guy is quadratic because it has x squared, right? Trinomial, true enough. It's a quadratic trinomial. And the reason why we need to check to see if it's a quadratic trinomial is quadratic trinomials tend to factor the same way every time. How do quadratic trinomials factor? What form do they take? Two binomials. That's correct. They factor into two binomials. So we can kind of set the infrastructure for how the quadratic trinomial factors. Now remember that there was two different flavors of quadratic trinomials, right? One flavor where it factors relatively easy, and then the other kind where the factorization was quite a bit more difficult. That was guess check, right? Now I'm not going to take time to rehash the difference between the two. I think they will naturally come up today. But factoring this trinomial in particular, I think we should first look at which one of the three terms should we look at? X squared, and ask ourselves, well, how does an x squared factor? What two factors give me x squared?
X and X.
X and X, and that fills in the first two factors of my binomials. Then who should I look at?
3.
Close.
Negative 3.
Negative 3. Make sure we look at a negative 3, because that's going to ask us what two factors multiply to negative 3. We don't got very many choices. Negative 1 times 3, negative 3 times 1, and then how do we know which one to pick? They got to add to that 2, right? They got to add to that 2x. So in this case, if we add these guys up, negative 1 and 3 does give me 2. That's the correct pair of factors there. Very good. Negative 1, positive 3. That is the correct factorization of this quadratic trinomial. Now, one of the things I tried to emphasize on Tuesday is the beauty of factoring is that it takes us into something that's nonlinear. Right? Remember, these polynomials are kind of a subset. They're underneath the umbrella of things that are nonlinear. Look what happened when we took a nonlinear trinomial and we factored it. Look at what the factors are. Do you see what it does is it breaks it into factors, and these two factors are linear. Do you see them? See this guy right here? See how he's linear? Because it doesn't have that exponent of 2. It's linear, and linear expressions and linear equations and linear functions are much easier to deal with. That's why we didn't waste our time at all, did we? We took something that was nonlinear and we rearranged it into two things that were linear. That's, I think that's probably the most, and we'll see that really in action today. That's one of the most important things we can do is take something that's nonlinear and break it down into linear factors. Mission accomplished there. We weren't done. There was one more type of factoring. Yeah, it was a difference of squares where you had two terms that were perfect squares. Right? And for example, if we had x squared minus y squared, x squared minus y squared again factors into two binomials. I don't know if you remember on Tuesday, but I said the only type of factorization that doesn't factor into two binomials is this GCF. And that GCF is, I think that we practiced it enough on Tuesday where we kind of got the feel that the GCF is when you have a monomial on the outside of the parentheses, and then you have a big polynomial on the inside of the parentheses. That's the only type of factorization that's not two binomials. The other two are two binomials. We got
X and X.
X and X. There's no guessing about it, right? They just split up into their perfect squares. X, X.
Positive Y, negative Y.
Y, Y, that's good. And the sign should be opposite. So if you want to go plus, minus, that's fine. Or minus, plus, either way. Okay, that's good. And that is, that's where we finished on Tuesday. We finished talking about how we can deal with these nonlinear expressions. So I think naturally what's going to come about today is going to be the next step. You can kind of see that where we're headed today is we're headed to this next category, we're going to be talking about nonlinear polynomials. Right? So that's where we're going today. Hopefully you can kind of see the bigger picture of a trend that happens. Please listen. Okay? Listen, please. The trend that happens is you can't deal with equations until you learn to deal with expressions. You have to know how to deal with expressions before you deal with equations. And really, you have to know how to deal with equations before you get to functions. Okay? So these descriptions aren't isolated. It's not like you learn one and then you learn another and then you learn another. They're very sequential in that you have to know how to do one before you get to the other. Okay? So I just wanted to make sure that you kind of see the big picture and how these three descriptions build on each other. Okay? And now I think we're ready to put that second brick in our building of dealing with nonlinear polynomials. Okay. So let's get started with that. Where's the infamous eraser? Am I going to have to go back to
Yeah.
old school?
It's kind of funny though. Where did it go?
While I'm thinking about it, I want to remind you guys, I made this announcement on Tuesday, that February 12th, I think that's the correct date, February 12th, we're not going to have class. I'm going to be in Frankfurt on that day. So if you haven't made a note of that, please do so. That's a week from this coming Tuesday. Okay. To get us going and talking about these polynomial equations, we talked about expressions enough. To get us going talking about these polynomial equations, I want you to tell me about this guy. Okay, I want you to complete this thought. Tell me about what happens if two values, I don't care what they are, I'm going to make them very generic, okay? They're just going to be any number you want. Two values, I don't care what, I'll call them A and B. Okay, and they're multiplying. If they're multiplying, these two values are called factors, right, because they're multiplying. If these two values multiply together, and the result of multiplication is 0, I don't know what they are, but I know that when they multiply, the result is 0. Then, is there anything that we can, say about A, or that we can say about B, if we know that they multiply to 0?
One of them is 0.
One of them 0, right? Or both of them. Is that true with any other value other than 0? Let's just go to a thought bubble here. Is that true with, like, if A times B equals 1? Does one of them have to be 1? I don't think so. Can somebody give me a counterexample there? Don't focus on just whole numbers. Go to other numbers. There's other numbers out there other than just good old-fashioned whole numbers. Think about fractions.
Yeah.
Yeah, 0.5 times 2, or a half times 2. That's very good. A half times 2 is 1. Right? So this property, this phenomena, is unique to 0. It doesn't happen unless the two values being multiplied is equal to 0. If two values multiply to 0, then either the first factor is 0, or the second factor is 0. That's not true with any other value other than 0. Okay, this is called the zero factor property. I think your textbook calls it something fancy here, the principle of zero products. This is called the zero factor property, is the terminology I learned. Zero factor property. What's the zero factor property? It says if two factors multiply to give you 0, then one of them has to be 0. I want to show you something else though, okay? I want to show you that this is only true with factors, values that multiply. It is not true. Please listen. It is not true with terms. If two values add to give you 0, I can't say anything about A or B. They have to be factors. Okay? So that means if you don't have factors, then it's pretty useless. You know what the good news is the good news is that Tuesday you guys learned how to create factors. That's what we just talked about on our little review. You've learned how to create factors. So we're going to use that to our advantage. So now what we can do is now we can start dealing with equations, because we now know that factors give us this interesting property, right? And this interesting property is if two values multiply giving 0, then one of them is 0. Let's use that to our advantage and deal with these polynomial equations. Let me show you an example. Remember, we've already seen this quadratic trinomial. Right? We've already talked about him. Right? That was in our review. But now what I want you to do is I want you to consider this quadratic trinomial as an equation when that equation equals 0. Now, remember, there is something special about having an equation equal to 0. What was special about saying an equation equal to 0 is if you can somehow create factors. Think about what I just erased, folks. What I just erased was if you have two factors like A times B and it equals 0, then I know something about A or B. Right? I know something about A or B. These, what you're looking at here, they are not factors. Remember what they are. They're terms, right? And in particular, they're 3 terms. This is why it's called a trinomial. But I think that we can create factors. We know how to factor. We go through the GCF, quadratic trinomials, difference of squares. If we can create factors, then maybe we're on to something. Okay? Remember how this factor, we just did it. How did this factor? What was it?
Yeah.
X and X.
Minus 1 plus 3.
Minus 1 plus 3. That was it, right? It did the trick. That's very good. And it equals 0. Now look what we got. We got 2 factors, right? Our first factor, what's our first factor? Can you name it?
X minus 1.
X minus 1. Remember, factors are values that multiply. I don't know what the value is exactly, but I know it's some value minus 1. This is my first factor right here. It's binomial. X minus 1. My second factor, he is X plus 3. You see the 2 factors. They are multiplying. What did the 0 factor property say? It said if 2 values multiply, here's my 2 values. Boom and boom. If they multiply, and that multiplication equals 0, then what can we say? One of them has to be 0, right? So if these 2 values multiply to 0, then we can say either the first factor is 0. If this is true, then the first factor equals 0, right? Or what?
Second factor.
The second factor equals 0. Can we solve those 2 equations? Can you isolate x?
Yes.
Can you get x by itself there? Yes, because it's an equation you know about. What kind of equation are you looking at here? You're looking at a good old-fashioned
Algebraic equation.
This guy right here. Look at him. What kind of equation? Linear. Good old-fashioned linear equation, right? We know how to solve linear equations. It's one little algebra move. Do it. Plus 1. Yep. Add 1 to both sides. X can be 1, or we can solve that as well. He's linear. Minus 3. X can be negative 3. You know what, folks? Those 2 values of x will make that equation balance out. If you don't believe me, you can always check. You can always check, but I don't want to jump into the check without you appreciating what just happened. Okay? You know, we can get really excited and get to the check, but you need to digest what you just did, okay? What just happened is we solved something that was nonlinear. Okay? We went to that second stage where we dealt with something that was a nonlinear polynomial, and we learned how to deal with that expression. How do we deal with it? We factored it, and then we used one more property, the zero factor property. All right? That zero factor property tells us if you do have factors, and we do, and they equal 0, then each factor is equal to 0 separately. Then we can solve that because it's linear. If you want to check to be sure you're right, you can do that. I mean, we can go back up to our original quadratic trinomial and check, and be sure if we plug in a 1 that it really does. Look at my original equation here. If I think that that the equation really is true, or really is balanced when x is 1, it better check out. Let's look and see what we got here. X squared plus 2x minus 3. I think that x value is 1. Let's quickly do the computation here. 1 squared is
1. Plus
Don't be
2.
tempted to say 2. Is that true? Let's see here. If you got $1 and then you add 2 more and then you take, yep. All right, 3, take away 3. Yeah, that checks out. It's true. And then we can do the same thing for the other x value. There's my original. I think x is -3. Careful, -3 squared, you know what that means, right? That means
Positive.
-3 times negative. Make sure you get that negative times negative to be a positive. Yeah, that's a positive 9. 2 and -3 multiplies to -6. Let's see if that's true. If you've got 9, take away 6, that's 3 minus 3. I think that's true, right? 3 minus 3 is 0.
Mm-hmm.
Yeah, that checks out. That checks out as well.
That's kind of cool.
Let me show you something. If you think that's cool, you're about to get your socks rocked off right here, babe. Check this out. If something's linear, just real quick. There you go. Help me solve just real fast.
Add 3.
Add 3, right? So we're adding 3,
5.
and then divided 2. When things are linear, how many solutions should we expect?
1.
1. We should expect one value that makes it true. What we just had was we had a quadratic, right? That means x squared. If I'm saying quadratic, that means you have an x squared. And what we just had here is we had a quadratic. Remember, quadratic, it's not just x. It's x squared. And we did the hokey pokey. We found that x is 1 and x is -3. 2 solutions, right? There was 2 solutions here. That was kind of a natural byproduct of the zero factor property, okay? Remember, linear, it was just x. Quadratic, x squared. 1 solution and 2 solutions respectively, okay? You know where I'm going here? The next thing you'll learn about, probably in college algebra, are cubics. A cubic indicates that you have x cubed, right? Blah, 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 blah. X cubed. And then when you go through the process, guess how many solutions you're going to get? Typically, you'll get 3 solutions. And then if you dealt with x to the 4th, 4 solutions, it's a very interesting little property that the largest exponent gives you a really good clue of how many solutions to expect. Pretty interesting little tidbit of information there. All right. Yep, I thought so. All right. Let's take a look at Look at this guy. So what I want you to do is I want you to be able to look at an algebraic description and kind of make sure that you can categorize it. It needs to go into the appropriate folder in the brain. Okay? So when you look at that, what I want you to go through in your mind is I want you to be able to identify if it's an expression, equation, or function. Okay? So when I look at that, I know that this thing's an equation, right? It's an equation. And then the next thing you need to do is you need to categorize it further. You need to say, okay, is this thing linear or is it quadratic? Okay? Because if it's linear, then all we have to do is we just have to do some opposite operation things that we did over there. But if it's nonlinear, in particular if it's quadratic, then we have to do something fundamentally different, right? So let's categorize this. Here's an algebraic equation. What kind of algebraic equation? Quadratic, okay? How can we solve quadratics is we use the zero factor property, okay? The zero factor property says that my equation better equal zero factor property, right? So I better get this to equal 0. I want to give you a word of advice. When you get your equation equal to 0, why do we need equal to 0? Zero factor property. At all costs, keep the number, okay, this is the coefficient, right? Keep the coefficient on x squared positive. So I would not recommend subtracting 16x and get it over here. I want to keep this positive, so who needs to move is that 9 needs to move. Okay, let's go ahead and move it. Go ahead and move it for me. Yeah, you subtracted it over. That's good. And when you subtract it over, what's left on the right? 0. Perfect. This is nonlinear. Nonlinear equations need to be equal to 0. Okay? Now, the reason why we need them equal to 0 is that we can get factors because of the zero factor property. Okay? Let's get factors going here. Let's go through the GCF. Go through the GCF, see if there's anything that will divide into a 16 and a 9.
Nope. No.
Anything?
No.
No? Do they have a common variable? No. Okay, so no GCF. Is it a quadratic trinomial?
No.
No, it's close. It's a quadratic binomial. Now, so we can't do that. Okay, so we're down to our last option. Is it a difference of squares?
Yes.
Yes, perfect. It's a difference of squares. How does a difference of squares factor?
4x. Well, it's two binomials.
Two binomials, good. And then let's factor it. 4x and 4x. Good. Good. Negative 3, positive 3. And don't be bothered by the negative being first or second. It doesn't matter as long as the signs are opposite. Good. So this is the correct factorization. Why we got it factored is now we can use the zero factor property, which says if you have two values, two factors that are being multiplied, there they are, then what happens is either the first factor equals 0 or the second factor equals 0. And we can solve those. The reason why we can solve those is factoring boiled down a quadratic into its linear parts. Okay? It boiled down its factors into its linear parts. And we can solve these two separate linear equations. I hope. I think we can, right? All right, here we go. Yeah, we'll add 3 to get rid of the subtraction there. If we add 3 to 0, that gives me 3. And then one last thing, divide off the 4. So that tells me that if we put in a 3/4 up into the original quadratic, that will make the equation true. Okay? But there's one other solution. We could, subtract off the 3, right? Divide off of 4. So it could be 3/4 or negative 3/4.
This is really interesting. In perfect squares, is it always the inverse? Opposite sign, but the same answer practically?
You mean the opposite signs here, right?
Yeah.
Yeah, it is. Oh man, I can't resist. I know that it will take 2 or 3 minutes, but I can't resist. You know what it's like? It's like this, John. If you have, where am I at? Right here. Let's take it from here, right?
Mm-hmm.
Let me actually do a difference of squares that's a little bit more simplistic here. Let's do x squared minus 25 is 0, okay? How I want you to think about this difference of squares is I want you to think about it actually as a quadratic trinomial. Look at the middle term. There's no x's there. You see up in the original there was no x's? That's why this thing factors into two binomials. And then you need to find x and x, right? Just like we thought, x and x. Two numbers that multiply to negative 25 but add to 0. Negative 5, positive 5. It is a quadratic trinomial, but that middle term is actually 0. That's why you don't see it. So that's why they kind of factor the same way. It's I think if you can kind of view that and see why they both factor into two binomials, it can be helpful. Okay, so let's do one more, and then I'm going to make a transition on it. Okay, let's do one more. Let's do one more problem where we have to solve a nonlinear polynomial. Before we get going, let's review some key characteristics of solving nonlinear polynomials. Okay? When we have equations that are nonlinear, it's very important that the equation look like this. Something equal to 0, right? Something equal to 0, because if it's nonlinear, you're going to have to use a certain property. Do you remember the property's name? 0 factor property. That kind of tells you the whole story right there, right? It needs to be equal to 0, and you're going to eventually have to create 0 factor property, right? So you're going to need to set it equal to 0, then you're going to need to create factors, and that's going to get you on the road to solving. Let's take a look at this guy. He's going to start off wonderful, but he's going to end up being not so wonderful. Check it out. I'm kind of digging that right now. You know why? It's because it looks like that this thing is already factored. I mean, look at it. He is a pretty harmless little monomial there, right? X times, so he's a factor, he's being multiplied. X times x minus 4 looks like he was probably like the GCF. You envision that, it's like a GCF. And then it's being multiplied by another binomial. And boy, wouldn't it be wonderful if that thing equaled 0. Of course it's not. It is going to, this thing is going to be equal to 44. You know what factors, these two are factors, right? This is my first factor, this is my second factor. You know what factors do for you if it's not equal to 0? They cause your life to be much more difficult. Factors, like you got here on the left-hand side, do you absolutely no good unless the equation equals 0. There is no property that says 44 factor property or something of the sort. Okay, it's 0 factor property. Unless the equation equals 0, the factors actually shouldn't be there. The factors on the left side, they shouldn't be there, so we have to undo the factors. We actually have to physically do that multiplication because they don't do us any good because it's not equal to 0. Okay? So on the left-hand side, let's undo the factoring because they were pretty useless, right? And then we'll rearrange and we'll talk about it from there. But let's focus on the left. We've got to undo this because it wasn't equal to 0. Help me out.
X squared.
X squared, so you're undoing the factoring. This is good. X squared
4x
minus 4x
equals 44.
And that equals 44, okay? But now I think what we can do now is now we can rearrange this. Now we can identify it as a quadratic. Now we can rearrange this quadratic to be equal to 0. I think if I move that 44 to the other side with subtraction, it'll be okay. X squared minus 4x minus 44. Again, it cannot subtract any one of the previous two terms. And now it finally does equal 0. Now we got what we want. We got our We got our nonlinear equation equal to 0. Perfect. Now it is the 0 factor property that's going to help us. So that tells me I better factor. Let's see if we can't factor that left-hand side. Looks like it does not have a GCF. Well, look. It looks like it is a pretty classic quadratic trinomial. And I know how quadratic trinomials factor. They factor into two binomials. And the good thing is it's not guess check. I don't have to guess here. I know that it's going to be x and x. And now I have to find two values that multiply to negative 44 but add to a negative 4. Multiply to negative. When you think about multiplying to negative 44, I'm kind of naturally drawn to negative 11 and 4. I don't know about you, but I'm kind of naturally drawn to negative 11 and 4 or negative 4 and 11. I can't, let's see, I know that there's probably like, what, 2 and 22. I mean, I guess I'll give it some love, but anything else you can think of? Other than 1 and 44, I don't think that's going to be it. Out of those three, I'll put 4 up here. Out of those 4 pairs of factors, let's identify which one's going to work here. Looks like the first one, right? You see it? Yeah, that's not going to be it. Well, there's got to be something else then. Make sure I wrote it down right. That would do it. Try again. Guys, this is why you don't take notes in pen. Gotcha. All right. Okay, now we'll redigest that and see what we get. Well, the good news is that I already got the pairs up for you, and I think that now a pair will work. Yeah, it looks like the first one really does work now for real, right? If you add those guys up, that really does add to a negative 7. A good lesson, though, you know, really, if you come across a problem in your homework, and how many times have you just kept working and working and working, doesn't seem like it will ever come up, just double check the problem. You know, especially on the homework in my math lab, it keeps saying you're wrong, you're wrong. Just double check, make sure you wrote it correctly on your paper. It's, you know, it can happen, definitely happens to all of us. Not done. You know, this is, we made really good progress. We got rid of factorizations that were, frankly, quite a pain, and then we got it equal to 0. After some deliberation, we got it factored correctly. But we're not done. Remember, with equations, you need to figure out what value makes the equation true. I don't know yet, but I think that I can figure it out because of the 0 factor property. If two values multiply to give you 0, then either the first one, I'm not done. I don't know what value of x is going to make the equation true. Either this first factor is 0, or the second factor is 0. Yeah, and I think from here it's just downhill. It's just making sure that we finish our task, right? Just isolate the y value. Add 11. 0 and 11 gives me 11. Or negative 4, right? 4 or 0 to equal 4 is negative 4. And again, if you want to check yourself, go for it. I think that that it will work.
So say the problem really was a negative 4. Would you just simply stop there because you couldn't factor it? Would you ever?
Yeah. Wow. Oh boy, that's a good transition question. I guess the question, in case you didn't hear it or you didn't completely digest it, the question was, what happens if you have a quadratic that won't factor? Do we throw up our hands and say, well, it doesn't factor, that must mean that there's no solution? This is the perfect transition into what's going to happen next week. Next week, what we're going to do is we're going to be able to solve any quadratic, whether it factors or not, okay? if we have a quadratic that factors, I think that we can do it now. We know kind of the basic structure of how to solve a quadratic that factors. But if they don't factor, that's a problem, okay? And that requires us to do something else. And that something else that we're going to be doing next week requires us to have a skill set that I want to be sure that you have. And I don't know if you have it or not. Maybe some of you do, maybe some of you don't. But when we come back next week, I want to be sure that we're all on the same page and have this one ability that we're going to need to have next week that's going to allow us to solve quadratics that don't factor. Okay? So in today's lecture, what we're going to do is we're going to make a transition. And the transition that we're going to make is I want to teach you how to deal with square roots. And that may seem way off the topic. But the reason why we're dealing with square roots today is because next week, when we deal with quadratics that don't factor, we're going to have a really strong foundation with square roots. And if we don't have that foundation, then it's going to be a long week next week, okay? So for the next 20 minutes, okay, I want to talk to you about square roots, and it seems like it's going to be a little disconnected from this stuff, but remember why we're talking about square roots is to prepare us for next week. And next week we're going to be talking about these quadratics that don't factor. If they don't factor, the zero factor property isn't much good, is it? Okay? So let's go ahead and make that transition. Everybody with me? Kind of following where we're going now? Okay. So yeah, maybe in your notes put a carve out a special spot for these square roots. We better know how to deal with square roots so that we can finish what we need to finish with quadratics. And I think next time we meet, we will be able to complete our task with these quadratics that don't factor. Back in the day when they didn't have fancy word processors, okay, and they typed mathematical papers, and they wanted to type something that dealt with square roots. You know, old typewriters don't really have a square root key like we do, right? So back in the day when they dealt with square roots, they didn't have this square root key on the typewriter. So how they typed it, I don't even know where this thing started to evolve, but they typed it like this. They typed a good old-fashioned R, and then after that R, they would type in some letters and numbers, but that R indicated that it was a root, or a square root. And then evolution started to take its toll, and this R grew a tail, started to evolve, and so now, mathematically, when we deal with square roots, it's this R symbol that has grown a tail. And so if we deal with things like the square root of 4, that square root of 4 doesn't really tell you to do anything. It asks a question. Square root of 4 asks, what number squared gives you 4? Yeah, and that's why the answer is 2. So this doesn't tell you to do something, it asks a question. It says, what number squared gives us 4? And I think now maybe, after we see that question, perhaps now we can draw back on, well, now I understand why we're dealing with square roots, and previously we were dealing with x squared, because it seems like x squared and these square roots have a direct relation somehow. So we better know how to deal with these square roots so that we can eventually maybe complete our task with things that are quadratic. And by quadratic, I mean squared, right? Squared. Okay. Well, this is fun and all, but let's look at another example. If I wanted to know, like, what's the square root of 8? what that asks is it asks what number squared gives us 8. I'm glad to see that we grabbed the calculator, and when we grab the calculator, we check to see what it gives us. If you have your calculator, let's make sure that we know how to find the square root of 8. And when you find the square root of 8, it's not going to look pretty. Yeah. Did anybody have a scientific calculator and having difficulty finding the square root? I can help you in 10 seconds, I promise. Anybody else having some difficulty with square roots? So you can see that square root of 8 is a decimal you don't want to deal with, right? It is a decimal that seemingly has no pattern to it. And it's true. The square root of 8, what's it like, 2.4 something?
2.828.27.
Perfect. Good. That's very good. Yeah, nasty decimal, right? And that decimal doesn't have any sort of repeating pattern. It's called an irrational decimal. There's no pattern, and it never stops. I know it stops on your calculator because it's ran out of room, but it is a decimal that never stops and it never repeats. You don't want to go there. Okay? You do not want to take this to a decimal. The decimal is a bad idea. You'll lose precision. So what we want to do is we want to take this square root and we want to simplify it as much as possible. And we're not going to be able to simplify it with one cute little number like that. Okay? This guy was nice in that he was a perfect square root. Square root of 4, and the calculator, type it in, it comes out to be a nice 2. Okay? Not the case here. Let me teach you how to simplify square roots. Okay? The key to simplifying square roots is a factor tree. I'm assuming we factor treed before. The factor tree goes something like this. You start with the number that you're wanting to simplify, and then you take, I guess for lack of a better word, you take tree branches and branch off to two numbers that multiply to give you that number, any two numbers that multiply to give you 8, other than 8 and 1. Okay? So I think the obvious place to go is going to be
2 and 4.
2 and 4. And then we keep going until we can't go any further. Let's go to 2. Two numbers that multiply to 2 other than 2 and 1? There's none. And if there's none, what we do is we circle. He's done. Okay? Go to the next one. Two numbers that multiply to 4 other than 4 and 1? 2 and 2. And then we found out that that 2 cannot break down any further. They are prime. Okay? So now what we do is we focus our attention on the values that we circled. And what we've circled is we've circled 2, 2, and 2. That means to get 8, you can multiply 2 times 2 times, that's true, right? 2 times 2 times 2 is 8. Now watch what we do.
Will it be 2 to the 3rd power?
It is 2 to the 3rd power, but check this out. When we rewrite the square root of 8, what we want to do is we want to rewrite the values that are circled, if at all possible, in terms of squares. In terms of squares. Now, I get that we could write this as 2 to the 3rd, right? 2 times, we could write that as 2 to the 3rd. It's true. But that's not helpful. What we want to do is we want to write that as 2 squared. I'll tell you why in just a second. 2 squared times 2. Now, here's why we did not write that as 2 to the 3rd. And it's an important principle. It's this. Square roots. You see it there. Square roots and squares are opposite operations. They're opposite operations. They, in effect, undo each other, just like addition undoes subtraction. We've seen it all day today. Addition undoes subtraction. What else are opposite operations? What other two operations do we know about?
Multiplication,
division, exponents, and roots. Square roots undo squares. Square roots do not undo cubes. That's the reason why I didn't write it 2 to the 3rd. It does no good with a cube. It will undo squares, right? Watch how it's going to undo a square. The square root and the square, I'm not going to physically do anything. Yeah, I am. It will physically cancel each other. So what's left over then is just that base. This base 2 is free. It's free from the square root. It's free from the square. It's free. Okay? How about this guy? Is he free? The answer is no, because it does not have a square, right? It is still trapped under the square root. What can liberate the number from a square root is a square, right? It can be freed from the square root only if it has a square. This does not have a square. It stays on the inside. How can the square root of 8 be simplified? 2 times the square root of 2. That's as good as it gets. Okay? That's going to take some practice. I don't expect you to be professional square root simplifiers now. Let's keep practicing.
Does that really work? It doesn't look like it does.
It does. I promise. Wait. Square root of 120. Grab your calculator. See if the square root of 120 comes out to be something nice and clean, or if it comes out to be something nasty. If it comes out to be a nasty decimal, we need to jump into a factor tree. Okay? Clean or dirty? Dirty. Okay, so we jump into a factor tree. Now look, I don't care where you start. You can go 12 times 10. You can do 20 times 6. You can do 2 times 60. I don't care where you start. To simplify a square root, you just get the factor tree rolling, okay? What you cannot do is 120 times 1, okay? Anything that multiplies to give you 120. Where do you want to start? 12 and 10. Okay, let's keep 6 and 2. I think 2's done. 3 and 2. 3's done, 2's done. There's no value that multiplies to give you 3 other than 3 and 1. All right, we're not done because we still got 10 over here. 5 and 2. We're done.
Okay, I got a question.
Yeah, go for it.
The 12, why couldn't you put 4 and 3?
Good question. 4 and 3 factors to 2 and 2. What? 2, 2, 3. 2, 2, 3.
So it still would work.
Still would work. Yeah, still would work. Okay. All right. So that's fun and all, but how does that help me? Let's go and let's rewrite. Let's rewrite under the square root. And what we're really after, what's really going to help us is something that is squared, right? Because if something's squared, it's going to free it up from the square root. That's what makes it more simplistic. If we can grab squares that free up the number from the square root. Let's see if we've got any here. Yeah, we got 2 squared. I don't know where you're looking. I'm looking right here. See these 2? 2 squared. That's 2 times 2. I'm down with that. That's good. Looks like we got a few other values though. We got another factor of 2. I don't care what order you go in. There's another factor of 2. A factor of 3. And a factor of 5. Notice I'm only looking at the values that are circled. I'm only looking at the values that I circled. And now let's see what can come out. Is there any base? We got base 2, base 2, base 3, base 5. We got 4 different bases. Of those 4 bases, can any of those bases come on the outside of that square root? The 2, right? Because that 2 can get freed up from the square root because of the square. The square undoes the square root. This square root and this square free that base 2. You might say, well, where did the square root go? It canceled the square. Or the square's gone as well. It got canceled by the square root. What's on the inside? 2 times 3 times 5. The square root of 120 ends up being 2 times the square root of, and we'll multiply those out, that's 6 times 5, it's 30, yeah. Multiply those, you get 30. That's how we simplify square roots, folks, is we do the factor tree. And when we do the factor tree, the purpose of doing the factor tree is to try to find squares that undo square roots. Okay?
Now, can I ask you to elaborate on that mathematical operation there? And
Sorry?
can I ask you to prove to me that 2 times the square root of 2
Yeah.
equals 8?
Absolutely. So in the calculator, I want you to calculate square root of 120. Okay? It's going to give you a nasty decimal.
Yeah.
Okay, what's that give you?
10.95445.
Okay, 10.95 something, right? Okay, now what I want you to do is I want you to find the square root of 30.
That's 5.47.
Okay, and then times 2.
10.95.
Uh-huh. Yeah, it's more simplistic. The inside that square root is cleaner, right? Pretty
Okay,
cool.
that makes sense.
Very nice.
Thank you.
All right, one more, and then I will. I'll send you the break. Let's take a look at this guy. How about 6 times the square root of 40? 6 times the square root of 40. I guess you could check in the calculator. When you check in the calculator, all you need to check is square root of 40. And when you check square root of 40, if that comes out clean, well then hot dog, all you do is multiply it by 6. Okay, well all right. So if it's not what we want it to be, we go and we factor tree it. Okay, factor tree 40. Don't pay any mind to the 6 right now. Just factor tree 40. I don't care if you go 8 and 5 or 4 and 10 or 2 and 20. I'm going to go 4 and 10. If you want to do something else, go for it. Then 2 and 2 after that. And then 2 and 5. All right. So just the factor tree. If you go to the factor tree a different route, don't sweat it. What the factor tree does for you is it kind of allows you to see if there's any perfect squares. So the square root of 40 ends up being, just look at the numbers that are circled. Don't worry about any of the other values except the ones that are circled. 2 squared, I'm with you. Times 2, so you did 2 squared, that's those 2, times 2, times 5. You know what, I've put him off long enough. He's on the outside. I'm just going to put him on the outside still yet. Okay, let's clean it up. Anybody come on the outside here? 2. A 2, right?
So 2 times 6 would be 12.
2 times 6 on the inside, 2 times 5. After all is said and done, I'm looking at 12 square root of 10.
Yeah.
12 times square root of 10.
Now, if let's see, underneath the 4 you do 2 and 2, you turn it into 2 squared. Underneath the 10, you turn it to 2 times 5. If that was also a 4, would you also make that 2 squared times 2 squared?
Mm-hmm. Yeah. So 2 squared times 2. So this would come out, and this would come out.
Okay.
Yeah. Yeah, it's a good question. One more thing before we break. It's true that sometimes you might have more than one factor that comes on the outside. Hypothetically, if you have a couple of factors in here that are squared, I mean, that's fine. You can take more than one factor on the outside. On the outside, this 2 would come out, this 2 would come out, this 3 would come out, that 7 has to stay on the inside. That would be 4, that would be 12 times the square root of 7 is what that would be. Sometimes there's more than one factor that comes on the outside. Okay? That would be 12 square root of 7. Okay, good. So let's go ahead and take 15 when you come back. There's going to be a few problems that deal with solving quadratics by factoring. And then there's going to be a few problems that talk about simplifying square roots. Unfortunately, The answer key I had to manipulate some of the problems, so the answer key doesn't do us much good. I'll try to create one later on. Okay, I'll see you guys.